Welcome to lamps and lasers. These are the sources of light that we're going to use for our spectrophotometers. So let's start with lamps. A tungsten lamp at around 3000 Kelvin emits useful light from around 320 nanometers to 2500 nanometers or so. This makes it useful for visible and near IR spectrophotometry. But ultraviolet spectroscopy usually uses a deuterium arc lamp. This has a controlled electronic discharge that causes our deuterium D2 to dissociate and emit light in the 110 to 400 nanometer range. A tungsten lamp and a deuterium arc lamp can then be used in conjunction in a UV-VIS spectrophotometer, where a mirror is switching between our two sources at the wavelength at which the two sources have the same intensity, which is 360 nanometers. And an electric discharge lamp can be used to generate light of specific wavelengths corresponding to the atomic emission spectrum of the gas that's inside that lamp. Mercury and xenon are often used here. We can also use light-emitting diodes, or LEDs, to generate narrow bands of visible light and near IR light. Alternately, we can use a silicon carbide glow bar, which is often used to emit infrared light in the 4000 to 2000 wave number range. This glow bar operates at 1500 Kelvin and emits approximately the same spectrum as a 1000 Kelvin black body. So now let's turn to lasers. The word laser is an acronym for light amplification by stimulated emission of radiation. And we can see a few lasers here. Now, be really careful with lasers. They're incredibly bright at the wavelengths that they emit at. So you need to be really careful not to look at any laser or to point a laser into somebody else's eyes. Now, lasers emit isolated lines of just a single wavelength. For example, a laser with a wavelength of 3 microns may have a bandwidth, this is the range of wavelengths, somewhere between 10 to the minus 14 to 10 to the minus 8 microns. Note that the bandwidth then is measured where the radiant power falls to half the peak value. This is the full width at half maximum. Again, lasers are incredibly intense. The intensity of even a very low power laser at its output wavelength is 10 to the 13 times brighter than the sun at its most intense wavelength. Now, naturally, the sun emits at very many wavelengths instead of just a single wavelength, which means that the total brightness of the sun is far, far higher than even our most powerful lasers are. So what we're talking about here by saying that even a low power laser is brighter than the sun, what we mean is within that spectrum range, if you look at the intensity over just a very narrow band, the intensity of that laser is going to be way higher than the intensity of sunlight at that band. Now, the sunlight is over a much broader band than the laser light is, and thus the total amount of energy coming from the sun at all wavelengths is way higher than any laser we can make. So let's talk about some properties of light coming out of lasers. Laser light is collimated, which means that it's parallel. That is, it doesn't diverge as light coming from a light bulb does. So we can have collimated light, which is parallel. We can have diverging light, where the rays move away from each other. We can have converging light, where those light rays are focused onto a single point, and then past that point, then they diverge. And generally, the divergence of laser light is less than 0.05 degrees. Now, laser light is usually plane polarized. That is, the electric field oscillates in a plane perpendicular to the propagation direction. So if we have unpolarized light, like this, or like sunlight is, and we pass that through a polarizer, a plane polarizing filter, we'll get our light waves, that electromagnetic wave, will all be moving in the same direction. In this case, it happens to be vertically polarized, so the electric field of each wave is moving in the vertical direction. Laser light is also coherent. That is, all waves emitted are in phase with each other. So with laser light, if we have 3 photons, 3 waves, those waves are all going to be oscillating in the same direction at the same time. If we have something like an LED, that light is not coherent. Those waves are out of phase. And if we have something like sunlight, then we have lots of different waves with different wavelengths. Those are also not in phase. So now let's look at how lasers work. We have molecules in the ground state E0, those are down here, of our lasing medium. So note that down here we've got some region here containing our lasing medium. We have to put some energy in. So the molecules in the ground state E0 of our lasing medium are pumped to excited state E3. So they're pumped up there. That's this energy coming in here. And they're pumped using radiation from a lamp or from an electric discharge. Our molecules are then quickly relaxing from E3 down here through vibrational relaxation to state E2. So E3 has a very short lifetime, E2 has a long lifetime. Now, molecules in E2 can then emit a photon as they transition down to state E1, and E1 is that state there. And now molecules in E1 then quickly relax back down to our ground state E0. And this is crucial because lasing requires a state of population inversion, whereby a higher energy state has a larger population than a lower energy state. So the Boltzmann distribution predicts that if we increase the energy of our state, then at thermal equilibrium, the higher energy state has a lower population. But in order to have any lasing occur, we have to have our higher energy state with a larger population than our lower energy state. So when a photon has exactly the same energy as the difference between two states of a molecule, so we're looking at this difference in energy here to there, from E2 to E1, then that photon that comes in can be absorbed by a molecule in the lower energy state, transitioning from E1 up to E2, or that photon can stimulate a molecule in the higher energy state, E2, to emit a second photon as it transitions down to E1. And this emission of the second photon is called stimulated emission because it's been stimulated by that first photon coming in. So note here that the phase and polarization of our emitted photon, this second photon, match those of our incident photon, that first photon coming in. So now we have two photons that are in phase, they're polarized in the same way, they have the same energy, and when there's population inversion, then one photon can stimulate the emission of many other photons as it travels through the lasing medium. Now, we have to have a state of population inversion, because if we don't, if we have more molecules in state E1 than in state E2, then as a photon comes in, we're more likely to have our molecule absorb that photon and move up to E2 than we will a molecule that's already excited move down. And this is why we have 4 different energy levels involved, because if we pump up to the top one and it quickly decays down to E2, and then molecules sit in E2 for a long time, and then once they transition back down to E1, then they quickly go away, back down into E0. That means that not very molecules are sitting here in E1. There aren't very many molecules that can absorb that photon. But if we have a bunch of molecules sitting in E2, then there are a bunch of molecules that can release a photon, and that is what allows our laser to work. So a laser requires some energy source. This is our pump, and that's over here. We're putting some energy in. And then on one end of the laser, we have a mirror that reflects all light, and that's what we have over here. So this is a mirror that reflects 100% of our light. There's 0% of the light getting through it. And now at the other end of our lasing cavity, we have a mirror that reflects only 99% of the light, but it allows 1% of our light through. And this means that photons with energy E2 minus E1 will bounce back and forth between our two mirrors and stimulate the emission of a large number of photons on every pass, and then just 1% of our light is coming out. And that 1% of light coming out is then our laser output. So there are a number of different common lasers, and some of them, not all of them, but some of them are the helium neon laser at 632.8 nanometers. This is a red laser. We have argon at 454.6 nanometers. We've got some dye lasers, and these can operate at various wavelengths depending on the dye. We've got ruby, which operates at 694.3 nanometers. We've got a neodymium YAG laser at 1.064 microns. And then we've got some laser diodes, again at various wavelengths. Now, laser diodes achieve population inversion by a large electric field across a p-n junction in a semiconductor. Now, laser diodes are available for wavelengths between 360 nanometers and 3,330 nanometers. So that was lamps and lasers, sources of light that we're going to use in our spectrophotometer.